Okay, so in the previous lecture, I talked about free body diagrams. Let me remind you. The idea is that if you have some object, like our hanging mass right here, you represent it by a dot, and then you draw an arrow that represents each force acting on it. So we have the string pulling up on it, we'll call that force 1. We have a spring pulling to the right, we'll call that F sub s. We've got gravity pulling down on it, F sub g, and then we've got this F2, the force with which that string is pulling it on it to the left. And we deduced by Newton's second law that implied that the force of gravity has to be equal to the force 1 so that the acceleration in the y direction can be 0. And we also deduced that the force with which the spring is pulling on it is equal to F2 so that the acceleration in the x direction is equal to 0. Okay, that's where we arrived at last time. Now, I want to highlight something that's very important here, and that is when we consider Newton's third law. So what is Newton's third law? Newton's third law says that for every force, there is an equal and opposite force, or for every action, there's an equal and opposite reaction. Now, what are the equal and opposite forces in the sense of Newton's third law for each of these forces? So in other words, each of these forces that I've drawn here must have an equal and opposite force in the sense of Newton's third law. I'm going to try to identify what the equal and opposite force is for each of these. So what is the equal and opposite force for each of these in the sense of Newton's third law? Newton's third law. That's the question we're going to ask. Now, one would be tempted, and most are, to say, well, force 1 is equal and opposite force g. Those are equal and opposite forces. And F2 is equal in strength and opposite in the direction to F sub s. So F2 and F sub s are equal and opposite forces in the sense of Newton's third law. But one would be incorrect. That is not correct. It is true that F1 happens to be equal in size and opposite in direction to Fg. And it is also true that F sub s is equal in size and opposite in direction to F2, but this is not because of Newton's third law. We know that they're equal and opposite. We found that out by Newton's second law. Because the acceleration in the x direction must be 0, therefore this one must be equal in size and opposite in direction to this one. But they are not equal and opposite force pairs that we're talking about in Newton's third law. How do we know that? Well, because we know, according to Newton's third law, that any force has an equal and opposite force, but those equal and opposite forces act on different bodies. So for example, when Newton's talking about his third law, he says, if my finger is pushing on a stone, the stone is pushing on my finger. And those are the two forces that are equal and opposite. Notice finger pushes stone, and stone pushes finger. These are the equal and opposite forces he's talking about. But in this case, you've got two objects. You've got your finger, and you've got the stone. Your finger is pushing on the stone. This we might call force, force sub F. That's the finger pushing on the stone. And then the stone is pushing on your finger. That would be the force of the stone, let's say, pushing on your finger. Notice that these two forces are equal in size and opposite in direction, but they're acting on two different bodies. They're interaction forces. Those are the two equal and opposite forces that Newton is talking about. Now, looking back at our diagram, notice that all of these forces are acting on the same object. They are all acting on this mass. So while it's true that these happen to be equal in size and opposite in direction, they are not the equal and opposite forces that Newton is talking about. I can't emphasize this enough. This is an extremely important issue. If you don't get this straightened out in your mind, then you're going to have a lot of trouble in the future. Okay? So if Newton's third law is true, then there must be some other forces that are the equal and opposite forces for each of these four forces. So what are those other forces? Well, so what are the equal and opposite forces for each of these? Okay, so let's try to figure those out. What is the force that is equal and opposite to F sub s in the sense of Newton's third law? Well, you could do it this way. You could say, what is pulling on this mass? Well, you could say the spring is pulling on the mass. That is this force. That's F sub s. Well, you can just literally grammatically change it to the mass is pulling on the spring. So if the spring is pulling on the mass, then the mass is going to be pulling on the spring. Okay, so there are going to be two different objects. One is the mass, one is the spring. If the spring is pulling on the mass is pulling on the spring. For reasons you'll see in a moment, I'm going to phrase this slightly differently. I'm going to say, really, it's the shaft right here that is pulling on the mass using a spring. Kind of the spring is the thing that's communicating this force. So if this vertical shaft is pulling on the mass using the spring, then this mass must be pulling on the vertical shaft using the spring. So I'm going to draw another force right here. This is a free body diagram for this vertical shaft, and I'm going to call this Fs prime. That's not a derivative, it's just another force. So I'm going to write this out. So the shaft is pulling on the hanging mass using the spring. That is F sub s. And F sub s prime, you can do this just grammatically by changing the subject and the direct object. So the hanging mass is pulling on the shaft using the spring. Those are the equal and opposite forces that Newton is talking about in his third law. Notice they're acting on different objects. Okay, let's do this for the other forces. What's the equal and opposite force of F1? Well, maybe we call this the horizontal bar. Okay, so this is the shaft right here. This is the bar, just because I don't know what else to call it. Okay, so if the bar is pulling up on the mass using this string, then the mass must be pulling down on the bar using the string. So I'll call this F1 prime. So if F1 is the bar pulling up on the mass, I'm just going to say the mass instead of the hanging mass, using a string, then the equal and opposite force that Newton's talking about is F1 prime, and that is the mass pulling down on the bar using the string. Okay, good, getting the hang of it. What about over here? We've got another string over here, and the string kind of goes over this pulley, and we're pulling down right here. So I don't know how we're going to do this exactly. Maybe we'll say that the scale is pulling on the mass using the string, and on the other hand, the pulley kind of diverts the direction of this force. So I guess it's pulling up this way. These are the equal and opposite force pairs. I could have pulled it straight sideways, but I pulled it around the pulley. So F2 is the scale pulling on the mass. And F2 prime, that's this one right here, F2 prime is the mass pulling on the scale. Okay? And what about this one right here? That's a little bit tricky. So what is pulling down? You might say gravity is pulling down, right? And you'd be right, but how do we phrase this then? If gravity is pulling on the mass, then is the mass pulling on gravity? I mean, what is gravity an object? Well, no, and you'll see now why I was phrasing these other ones in the way that I did. So what is the other object that's being pulled on? Well, it's the Earth. So this is the Earth. So the Earth is pulling on this mass using gravity. So Fg would be the Earth pulling on the mass using gravity as the medium of communicating this force, in a similar way that the shaft was pulling on the mass using the spring as a medium. The Earth is pulling on this using gravity as a medium of this force. And so what's the equal and opposite force? Well, that mass is pulling up on the Earth using gravity. So Fg prime is the mass pulling on the Earth using gravity. So just as gravity pulls down on this mass, so too gravity is pulling up on the Earth, because this object is attracting the Earth. Notice that in Newton's third law, it has implicit in it the idea that gravity is a universal force. That is, if one object pulls on, if the Earth is pulling on something, that something must be pulling on the Earth. Okay, so there's sort of an implicit recognition of this mutual interaction between objects that's implied in Newton's third law.